The ocean, it is the heartbeat of our planet. It is the force that shapes our weather, feeds our cities, governs our climate, and hides mysteries so profound that even the most brilliant scientific minds have barely scratched the surface. Right now, as you sit watching this, waves are crashing on distant shores. Currents are moving billions of gallons of water across hemispheres. Creatures that have never seen sunlight are gliding through pressures so intense they would crush a submarine. And somewhere in a trench so deep that no human has ever touched its floor, something is alive, something is moving, something is thriving in conditions that we once believed impossible. You think you know the ocean, you have seen the beaches, you have watched the waves, perhaps you have even gone snorkeling on a reef or watched whales breach from a boat. But what you have seen, what any of us have seen, is merely the thinnest skin on the surface of something unimaginably vast. The ocean is not just water. It is a world, it is in many ways a universe of its own, layered and complex, teeming with life that defies everything we think we understand about biology, chemistry, and physics. Over the course of this documentary, we are going to take you on a journey, not just across the surface, but down, deep down into the darkest, coldest, most mysterious places on Earth. We will explore the creatures that glow in the dark, the mountains that dwarf Everest, the rivers that flow beneath the sea, and the terrifying reality of what happens when the ocean decides to remind us just how small we truly are. This is the deep unknown, and it starts right now. Let us begin with something that should humble every single one of us. The ocean covers more than 70% of the Earth's surface. Think about that. When you look at a globe, what you're mostly seeing is water. The continents, the landmasses, the mountains and deserts and forests and cities, all of that, everything that humanity has ever built, every empire, every civilization sits on less than 30% of this planet's face. The ocean dominates, it always has, and it always will, but covering 70% of the surface is only part of the story. What most people never consider is volume. The ocean does not just spread wide, it goes deep. The average depth of the ocean is approximately 12,100 feet. That is over 2 miles straight down. Imagine stacking nearly 8 Empire State Buildings on top of one another and sinking them beneath the waves. The top of the highest building would still not break the surface. That is the average. There are places where the ocean goes far, far deeper than that. Places where the water column extends nearly 7 miles below the surface. Places so deep and so dark that they might as well be on another planet. And here is the part that should truly astonish you. Despite all of our technology, despite satellites and submersibles and sonar and remotely operated vehicles, we have explored less than 5% of the ocean. Less than 5%. We have better maps of the surface of Mars than we do of our own ocean floor. We have sent more people into outer space than we have sent to the deepest parts of the sea. The ocean is right here, right beneath us, surrounding every continent, touching every shore, and it remains overwhelmingly unknown. That is not a failure of curiosity. It is a testament to the sheer, staggering scale of what we are dealing with. The ocean contains approximately 321 million cubic miles of water. If you could somehow collect all of the water in every river, every lake, every reservoir, every puddle on Earth, it would not amount to even a fraction of what the ocean holds. The ocean is the great reservoir. It is the dominant feature of this planet, and we are only beginning to understand it. Now let us talk about something that flows through the ocean like blood through veins, currents. You may have heard of the Gulf Stream, or perhaps the Kuroshio Current off the coast of Japan. But these are just the most famous examples of a global system that is so vast and so interconnected that scientists sometimes refer to it as the Great Ocean Conveyor Belt. The technical name is thermohaline circulation, and it is one of the most important processes on the planet. Here's how it works. Water near the poles becomes extremely cold. As seawater freezes into ice, the salt is left behind, making the surrounding water denser and heavier. This cold, salty, dense water sinks, plunging thousands of feet below the surface. As it sinks, it pushes other water out of the way, setting off a chain reaction that sends currents flowing along the ocean floor, creeping across entire ocean basins at a pace so slow it would make a snail look fast. Eventually, this deep water rises again in a process called upwelling. usually near the equator or along certain coastlines, bringing nutrients from the deep up to the surface where they fuel enormous blooms of phytoplankton. This circulation pattern is not just some interesting quirk of physics. It is the engine that drives our climate. Without the thermohaline circulation, the distribution of heat across the planet would be radically different. Regions that currently enjoy mild, temperate weather would be locked in ice. Tropical regions might become even hotter. The delicate balance that allows human civilization to exist as we know it depends in no small part on this invisible river of water flowing through the deep ocean. And that river moves a staggering amount of water. The Gulf Stream alone carries more water than all of the rivers on Earth combined. Every second, the Gulf Stream moves approximately 30 million cubic meters of water. That is more than 100 times the flow of the Amazon River, which is itself the largest river on the planet by volume. The Gulf Stream is a liquid highway, stretching from the tropics up toward the North Atlantic, carrying warm water and warm air with it. It is the reason that parts of Western Europe enjoy milder winters than places at similar latitudes on other continents. Without it, cities like London and Paris would experience winters far more brutal than anything their residents have ever known. But the ocean does not just move water, it moves heat. The ocean absorbs an enormous amount of the sun's energy. In fact, the top 10 feet of the ocean hold as much heat energy as the entire atmosphere. Let that sink in for a moment. The thin, shallow skin of the ocean, just the top 10 feet, contains more thermal energy than all the air swirling around the entire planet. The ocean is, in essence, a giant heat battery. It absorbs energy during the day and during warm seasons, stores it, and releases it slowly over time. This is why coastal areas tend to have milder climates than inland regions. The ocean moderates temperature. It softens the extremes. This heat absorption has another consequence that is becoming increasingly important in our modern era. As the planet warms due to rising levels of greenhouse gases, the ocean has been absorbing the vast majority of that excess heat. Scientists estimate that the ocean has absorbed more than 90% of the additional heat trapped by greenhouse gases since the middle of the 20th century. 90%. Without the ocean acting as a buffer, the surface temperature of the planet would have risen far more dramatically than it already has. In a sense, the ocean has been shielding us from the full consequences of our actions. But that shielding comes at a cost. The ocean is warming, and as it warms, it expands. This thermal expansion is one of the primary drivers of sea level rise. Now, speaking of what the ocean absorbs, it is not just heat. The ocean is also the planet's greatest carbon sink. Every year, the ocean absorbs roughly a quarter of all the carbon dioxide that humanity produces. Phytoplankton, those tiny, microscopic organisms floating near the surface, play a crucial role in this process. Through photosynthesis, they absorb carbon dioxide and release oxygen. In fact, phytoplankton produce between 50 and 80% of all the oxygen in Earth's atmosphere. Not trees, not forests, not grasslands. Tiny, invisible organisms floating in the top layer of the ocean. Every other breath you take, you owe to the sea. But when the ocean absorbs too much carbon dioxide, something dangerous happens. The CO2 reacts with seawater to form carbonic acid, which lowers the pH of the ocean. This process is called ocean acidification, and it is sometimes referred to as the other CO2 problem, because while most attention goes to the warming effects of carbon dioxide, the acidification of the ocean is a crisis of its own. As the water becomes more acidic, it becomes harder for marine organisms to build their shells and skeletons, which are made of calcium carbonate. Corals, shellfish, sea urchins, certain types of plankton, all of these creatures depend on their ability to extract calcium carbonate from the water. As the pH drops, that process becomes more and more difficult. In some cases, the water can become so acidic that it actually dissolves existing shells and coral structures. This brings us to one of the ocean's most spectacular and most threatened ecosystems, coral reefs. Coral reefs are sometimes called the rainforests of the sea, and for good reason. Although they cover less than 1% of the ocean floor, they are home to approximately 25% of all known marine species. 1% of the space, a quarter of all life. That is an extraordinary concentration of biodiversity. Corals themselves are animals. This surprises many people. They are not rocks, they are not plants. They are living animals, tiny polyps, each one no bigger than a pinhead, that build hard skeletons of calcium carbonate around themselves. Over centuries and millennia, these skeletons accumulate, layer upon layer, forming the massive reef structures that we see today. Some coral reef systems are so old and so large that they are visible from space. The Great Barrier Reef, the largest coral reef system on Earth, stretches for more than 1,400 miles along the northeastern coast of Australia. It is the largest single structure made by living organisms anywhere on the planet, but corals have a secret. They do not do it alone. Inside the tissue of most reef-building corals live tiny algae called zooxanthellae. These algae have a symbiotic relationship with the coral. The algae photosynthesize, using sunlight to produce sugars and other nutrients which they share with the coral. In return, the coral provides the algae with a safe home and access to the chemicals they need for photosynthesis. This partnership is what gives corals their vibrant colors, the greens, the blues, the purples, the oranges. Without the algae, corals appear white, they appear bleached, and that is exactly what is happening on reefs around the world. When ocean temperatures rise even slightly, just 1 or 2 degrees Celsius above normal, the corals become stressed and expel their zooxanthellae. Without the algae, the coral loses its color and, more importantly, its primary source of nutrition. If temperatures return to normal quickly enough, the algae can recolonize the coral and recovery is possible. But if the warm water persists for too long, the coral starves and dies. What is left behind is a white, lifeless skeleton, a ghost of what was once one of the most vibrant ecosystems on the planet. Mass bleaching events have become more frequent and more severe in recent decades. In some regions, up to 50% of coral cover has been lost within a single generation. Scientists warn that if current trends continue, we could lose the majority of the world's coral reefs by the middle of this century. The implications of that loss are difficult to overstate. Hundreds of millions of people around the world depend on coral reefs for food, for coastal protection, for tourism-based livelihoods. The fish that feed on reefs, the shellfish that grow among them, the sheer diversity of life that they support, all of it hangs in the balance. But let us leave the sunlit shallows for a moment and descend. Let us go deeper, because the ocean has layers, and each layer is its own world. The uppermost layer of the ocean, the part that receives sunlight, is called the epipelagic zone or the sunlight zone. It extends from the surface down to about 650 feet. This is where most of the ocean's photosynthesis occurs. This is where phytoplankton bloom, where fish school, where dolphins leap, where sea turtles glide. It is the part of the ocean that most people think of when they think of the sea, but it represents only a tiny fraction of the ocean's total volume. Below the sunlight zone lies the mesopelagic zone, sometimes called the twilight zone. It extends from about 650 feet down to around 3,300 feet. Here, sunlight fades to a dim bluish glow and then to darkness. The water is colder, the pressure is greater, and the creatures that live here are unlike anything found near the surface. Many of them have evolved the ability to produce their own light through a process called bioluminescence. They glow, they flash. They pulse with eerie blues and greens and reds. In the twilight zone, light is a language. It is used to attract mates, lure prey, confuse predators, and communicate in ways that scientists are still working to understand. One of the most remarkable phenomena in the twilight zone, and indeed in all of the ocean, is the diel vertical migration. Every single day as the sun sets, billions upon billions of creatures rise from the depths toward the surface to feed under the cover of darkness. And every morning, as the sun rises, they descend again, retreating into the safety of deeper, darker water. This is the largest migration of biomass on Earth. It happens every single day, and most people have never heard of it. The sheer volume of life involved is almost incomprehensible. Fish, squid, jellyfish, crustaceans, entire communities of organisms moving in synchrony, up and down, day after day, in a rhythm that has persisted for millions of years. Below the twilight zone, we enter the bathypelagic zone, the midnight zone. From 3,300 feet down to about 13,000 feet, there is no sunlight at all. None. It is absolute total darkness. The temperature hovers just above freezing. The pressure is immense, hundreds of times greater than at the surface, and yet life persists. Life, as it turns out, is extraordinarily stubborn. The creatures of the midnight zone are some of the strangest on the planet. There is the anglerfish, a creature so bizarre that it seems almost fictional. The female anglerfish has a bioluminescent lure dangling from her forehead, a glowing appendage that she uses to attract prey in the pitch darkness. When a smaller fish or shrimp comes to investigate the light, the anglerfish strikes with terrifying speed, swallowing prey up to twice her own size with a mouth that can expand like a trap. The male anglerfish, by contrast, is tiny, sometimes a tenth the size of the female. When a male finds a female, he bites into her flesh and fuses with her body, sharing her bloodstream and providing sperm in exchange for nutrients. He becomes, essentially, a permanent parasitic mate. It is one of the most extreme examples of sexual dimorphism in the entire animal kingdom. Then there is the giant squid. For centuries, sailors told stories of enormous tentacled beasts rising from the deep to attack ships. These stories were dismissed as mythology, as the drunken fantasies of superstitious seamen, but the giant squid is real, very real. It can grow to lengths of over 40 feet, with eyes the size of dinner plates, the largest eyes in the animal kingdom. Those enormous eyes are adapted to detect the faintest traces of light in the deep ocean, allowing the squid to spot predators and prey in near total darkness. Despite its size and notoriety, the giant squid was not filmed alive in its natural habitat until the early 21st century. Even now, almost everything we know about this creature comes from dead or dying specimens that have washed ashore or been caught in deep-sea trawl nets. The living giant squid remains one of the ocean's greatest enigmas, and below the midnight zone, things get even more extreme. The abyssopelagic zone, the abyss, extends from about 13,000 feet down to roughly 20,000 feet. The word abyss comes from a Greek word meaning bottomless, and when you consider what this zone is like, the name feels appropriate. The pressure here is crushing, over 600 times atmospheric pressure at the surface. The temperature is barely above freezing. Food is scarce. Most of the nutrition that reaches the abyss comes in the form of marine snow, a continuous slow rain of organic debris drifting down from the upper layers of the ocean. Dead plankton, fish feces, bits of decaying tissue, shed mucus, all of it sinks slowly through thousands of feet of water, and by the time it reaches the abyssal plain, most of the nutritional value has been consumed by organisms in the layers above. And yet, even here, there is life. Abyssal creatures have adapted to survive on almost nothing. Many of them are small, slow-moving, and incredibly energy efficient. They have slow metabolisms, they grow slowly, they reproduce infrequently, every calorie is precious, waste nothing, move only when necessary, wait for food to drift down from above, wait for an opportunity. In the abyss, patience is not a virtue. It is a survival strategy, but there is one more layer, one more zone. The deepest, most extreme environment in the entire ocean, the hadal zone. Named after Hades, the Greek god of the underworld, the hadal zone encompasses the ocean's trenches, those narrow, steep-sided gashes in the ocean floor where tectonic plates collide and one plate is forced beneath another. The deepest of these trenches is the Mariana Trench, located in the western Pacific Ocean. At its deepest point, a narrow slot called the Challenger Deep, the ocean floor lies approximately 36,000 feet below the surface. That is nearly 7 miles. If you placed Mount Everest at the bottom of the Mariana Trench, the peak would still be more than a mile below the surface of the water. Only a handful of people have ever traveled to the bottom of the Challenger Deep. The first were Jacques Piccard and Don Walsh, who descended in the bathyscaphe Trieste in January of 1960. Their dive took nearly 5 hours. When they reached the bottom, they were astonished to see a flatfish, proof that life existed even at the most extreme depth in the ocean. Decades later, filmmaker James Cameron made a solo descent in a specially designed submersible, reaching the bottom in about 2 hours and 40 minutes. And in more recent years, explorer Victor Vescovo made multiple dives to the Challenger Deep, discovering new species and, disturbingly, finding evidence of human-made trash, a plastic bag and candy wrappers, at the very bottom of the deepest place on Earth. That detail, trash at the bottom of the Mariana Trench, is worth pausing on. It tells us something profound about the reach of human impact. There is no place on this planet, no matter how remote, no matter how deep, no matter how inaccessible, that has escaped the influence of human activity. Microplastics have been found in every ocean, at every depth, in the tissues of creatures living in the most isolated environments imaginable. We have touched every corner of the sea, not with our presence, but with our waste. But the deep ocean is not just a barren, dark wasteland. It has features that rival and even surpass anything found on land. Consider the mid-ocean ridge system. Running like a seam through the Atlantic, Pacific, and Indian Oceans, the mid-ocean ridge is the longest mountain range on Earth. It stretches for more than 40,000 miles, wrapping around the planet like the stitching on a baseball. Most of it lies beneath thousands of feet of water, completely hidden from view. If you drain the ocean, the mid-ocean ridge would be the most prominent feature on the planet's surface, dwarfing the Himalayas, the Andes, and the Rockies combined. The mid-ocean ridge is not just a mountain range. It is a place where new ocean floor is being created. Along the ridge, tectonic plates are pulling apart, and molten rock from the Earth's mantle rises to fill the gap. As this magma cools, it solidifies into new crust, slowly pushing the older crust outward on either side. This process is called seafloor spreading, and it is one of the fundamental mechanisms of plate tectonics. The Atlantic Ocean is growing wider by about 1 inch per year, roughly the same rate at which your fingernails grow. It may seem insignificant, but over millions of years, that inch-by-inch expansion has transformed the planet's geography entirely. 200 million years ago, there was no Atlantic Ocean. The continents we now know as separate landmasses were joined together in a single supercontinent called Pangaea. The ocean we see today is a product of slow, relentless geological forces acting over timescales that are almost impossible for the human mind to grasp. Along the mid-ocean ridge and in other geologically active areas of the ocean floor, you will find one of the most extraordinary discoveries in the history of marine science: hydrothermal vents. First discovered in 1977 near the Galapagos Islands, hydrothermal vents are essentially underwater geysers. Superheated water, rich in dissolved minerals, erupts from cracks in the ocean floor at temperatures that can exceed 700 degrees Fahrenheit. The water does not boil because the immense pressure at those depths raises the boiling point far above what it is at the surface. When this superheated, mineral-laden water meets the near-freezing seawater of the deep ocean, the minerals precipitate out, forming towering chimney-like structures called black smokers. These chimneys can grow to heights of over 60 feet and belch plumes of dark, mineral-rich fluid that look like smoke. What makes hydrothermal vents truly revolutionary is the life that surrounds them. Before their discovery, scientists believed that all life on Earth ultimately depended on sunlight. Photosynthesis was the foundation of every food chain, every ecosystem, every web of life. But the communities living around hydrothermal vents shattered that assumption. Here, in total darkness, at crushing pressures, in water laced with toxic chemicals like hydrogen sulfide, life thrives. Not just survives, thrives. Giant tube worms, some over 6 feet long, cluster around the vents in dense forests. Eyeless shrimp swarm over the chimney surfaces. Ghostly white crabs pick through the mineral deposits. Mats of bacteria coat the rocks. The foundation of these ecosystems is not photosynthesis but chemosynthesis. Specialized bacteria use the chemical energy from hydrogen sulfide and other compounds spewing from the vents to produce organic molecules, food, from inorganic ingredients. These bacteria form the base of the food chain, supporting all the other organisms in the vent community. It was a discovery that fundamentally changed our understanding of where life can exist. If life can thrive in the superheated, toxic, lightless environment of a hydrothermal vent, then perhaps it can exist in similar environments elsewhere, on the ocean floors of Jupiter's moon Europa, or in the subsurface seas of Saturn's moon Enceladus. The discovery of hydrothermal vent communities did not just rewrite marine biology, it expanded the scope of where we look for life in the universe. Speaking of the strange and wondrous, let us talk about bioluminescence in greater detail, because it is one of the most magical phenomena in the natural world, and it is far more common than most people realize. Bioluminescence is the production and emission of light by a living organism. It is generated by a chemical reaction, typically involving a molecule called luciferin and an enzyme called luciferase. When luciferin is oxidized in the presence of luciferase, light is produced. And in the ocean, this ability is everywhere. It is estimated that between 76 and 90% of deep-sea creatures are bioluminescent. That is not a misprint. The vast majority of animals in the deep ocean can produce their own light. In a world without sunlight, light becomes the ultimate tool. Some organisms use bioluminescence to attract prey. The anglerfish and its glowing lure is perhaps the most famous example. Others use it to communicate with potential mates, flashing specific patterns that identify their species, their sex, and their readiness to reproduce. Still others use bioluminescence defensively, producing sudden flashes of light to startle predators, or releasing glowing clouds of bioluminescent fluid to confuse attackers, much like a squid releases ink. One of the most spectacular examples of bioluminescence visible from the surface is the phenomenon known as milky seas or mariel. Sailors have reported encountering vast stretches of ocean that glow with an eerie, pale blue-white light, sometimes extending for thousands of square miles. For centuries, these reports were treated with skepticism, but satellite imagery has confirmed their existence. The glow is believed to be caused by massive blooms of bioluminescent bacteria, possibly Vibrio parvae, which emit a continuous light when they reach a critical population density through a process called quorum sensing. The bacteria essentially vote. When enough of them are present, they all turn on their lights simultaneously. The result is a glow visible from space. On a smaller scale, many coastal waters around the world are home to bioluminescent dinoflagellates, single-celled organisms that flash blue-green light when disturbed. If you have ever been lucky enough to swim in bioluminescent waters at night, you know the experience is almost otherworldly. Every movement of your body, every stroke of your hand, every kick of your foot produces a burst of blue sparkles. Waves breaking on the beach glow. Fish dart through trails of light. It is one of the most breathtaking things the natural world has to offer, and it is caused by organisms so small that you cannot see them with the naked eye. Now let us shift our attention to some of the ocean's most iconic inhabitants, the blue whale, the largest animal ever known to have lived on Earth. Not the largest animal currently alive, the largest animal ever, larger than any dinosaur, larger than anything that has ever walked, crawled, swum, or flown on this planet. An adult blue whale can reach lengths of over 100 feet and weigh as much as 200 tons. Its heart is roughly the size of a small car and beats so powerfully that it can be detected from 2 miles away. Its tongue alone weighs as much as an elephant. A small child could crawl through its major arteries. And yet this behemoth, this titan of the deep, feeds almost exclusively on some of the smallest creatures in the ocean. Krill, tiny, shrimp-like crustaceans that rarely exceed 2 inches in length. A single blue whale can consume up to 6 tons of krill in a single day, filtering enormous mouthfuls of water through plates of baleen, comb-like structures made of keratin that hang from the upper jaw and strain food from the water. It is one of nature's great paradoxes, the largest animal on Earth sustained by one of the smallest. Blue whales are also among the loudest animals on the planet. Their low-frequency calls can reach volumes of up to 188 decibels, louder than a jet engine. These calls can travel through the water for hundreds, even thousands of miles. In the days before commercial shipping filled the ocean with noise, it is believed that blue whales could communicate across entire ocean basins. A whale in one hemisphere could, in theory, hear the call of another whale in a different hemisphere. The ocean was their telephone network, and their voices carried across distances that staggers the imagination. But here is a haunting footnote to that story. There is a whale, a single, solitary whale, that has been tracked by scientists for decades. It is known informally as the loneliest whale in the world, or the 52 Hz whale. Most blue whales vocalize at frequencies between 10 and 39 Hz. Fin whales call at around 20 Hz, but this whale calls at 52 Hz, a frequency that no other whale is known to use. Its calls have been detected repeatedly since the late 1980s, always from a single source, always alone. No other whale has ever been recorded responding to its calls. Scientists are not entirely sure what species it is. It may be a blue whale, a fin whale, or a hybrid of the two. What they do know is that it has been crossing the ocean for over 30 years, calling out into the void and never receiving an answer. Whether it is truly lonely in any emotional sense, we cannot say, but the image it conjures, a solitary voice in the vastness of the deep, forever unanswered, resonates with something profoundly human. Whales are not the only marine mammals that captivate us. Dolphins, those perennial favorites of the sea, are among the most intelligent creatures on the planet. Their brains are large and complex, with a neocortex that is, in some ways, more elaborate than our own. Dolphins are self-aware. They can recognize themselves in mirrors, a cognitive ability shared by only a small number of species, including humans, great apes, and elephants. They use tools. Some populations of bottlenose dolphins in certain regions carry marine sponges on their snouts to protect them while foraging on the rough ocean floor. They have been observed teaching this behavior to their young, a form of cultural transmission that was once thought to be uniquely human. Dolphins also have names. Each bottlenose dolphin develops its own unique signature whistle, a specific pattern of sounds that functions as an individual identifier. Other dolphins use this whistle to call out to specific individuals, much as we use names. When a dolphin hears its own signature whistle, it responds. When it hears the whistle of a close associate, it often approaches. This is not simple call and response. It is a form of social communication that implies a level of cognitive sophistication that continues to astonish researchers. And then there are the ocean's most feared predators, sharks. They have been swimming in the world's oceans for more than 400 million years. To put that in perspective, sharks predate trees. They predate dinosaurs by roughly 200 million years. They survived the Permian-Triassic extinction event, the worst mass extinction in Earth's history, which wiped out over 90% of all marine species. They survived the asteroid impact that killed the dinosaurs 66 million years ago. Through ice ages and warm periods, through continental drift and sea level changes, through every catastrophe this planet has thrown at them, sharks have endured. They are, in the truest sense, survivors. There are over 500 known species of sharks, and they range in size from the dwarf lantern shark, which fits in the palm of your hand, to the whale shark, the largest fish in the sea, which can grow to over 40 feet in length. Despite their fearsome reputation, the vast majority of sharks are not dangerous to humans. In fact, you are far more likely to be killed by a vending machine, a coconut falling from a tree, or a lightning strike than by a shark. Worldwide, shark attacks result in fewer than 10 deaths per year on average. Humans, on the other hand, kill an estimated 100 million sharks every year, primarily for their fins, which are used to make shark fin soup, a delicacy in certain cultures. This slaughter has driven many shark populations to the brink of collapse, with some species declining by more than 90% over the past few decades. The loss of sharks has consequences that ripple through entire ecosystems. As apex predators, sharks regulate the populations of species below them in the food chain. Remove the sharks and those populations explode, overgrazing on their own food sources and causing cascading effects that can fundamentally alter the structure and health of marine ecosystems. Scientists call this a trophic cascade, and it is a powerful illustration of how interconnected ocean life truly is. Let us talk about another predator, one that is less well known but equally fascinating. The orca or killer whale. Despite the name, orcas are not whales. They are the largest members of the dolphin family, and they are, by many measures, the most formidable predators in the ocean. Orcas hunt in coordinated groups called pods, using sophisticated strategies that are learned, not instinctive. Different populations of orcas have developed entirely different hunting techniques, passed down from generation to generation. Some populations specialize in hunting fish, using coordinated maneuvers to herd schools of herring into tight balls before stunning them with tail slaps. Other populations hunt marine mammals, seals, sea lions, even other whales. In certain regions, orcas have been observed creating waves to wash seals off ice floes, tipping the ice with precise, coordinated rushes of water. In other areas, orcas deliberately beach themselves to grab seal pups from the shore, then wriggle back into the water, a dangerous technique that mothers teach to their young through careful, patient instruction. Orcas have distinct cultures. Populations that live in the same waters but hunt different prey types have different vocalizations, different social structures, and different behaviors. They are genetically the same species, but culturally they are as different from one another as any two human societies. This cultural diversity within a single species is extraordinarily rare in the animal kingdom and speaks to the remarkable cognitive abilities of these animals. Now, let us turn our attention to the ocean floor itself, because it is not the flat, featureless plain that many people imagine. The ocean floor is a landscape as varied and dramatic as anything on the surface. There are mountains that rise tens of thousands of feet from the abyssal plain. There are canyons that cut deeper into the earth than the Grand Canyon. There are vast, flat plains of sediment that stretch for hundreds of miles. And there are features that have no analog on land, features that are unique to the ocean. One of the most remarkable of these features is the submarine canyon. These are deep, steep, walled valleys cut into the continental shelf and slope, often at the mouths of major rivers. The Monterey Canyon off the coast of California is one of the most studied. It is comparable in size and depth to the Grand Canyon, yet it lies entirely beneath the ocean's surface. Submarine canyons serve as conduits for sediment transport, channeling material from the continental shelf down into the deep ocean. They are also hotspots of biodiversity, providing a range of habitats and environmental conditions that support diverse communities of organisms. Then there are seamounts, underwater mountains that rise at least 3,300 feet from the ocean floor but do not break the surface. If they broke the surface, they would be islands. There are an estimated 100,000 seamounts in the world's oceans, though only a small fraction have been surveyed in any detail. Seamounts are biodiversity hotspots. Their steep sides create upwelling currents that bring nutrients from the deep, fueling productive ecosystems that attract everything from tiny invertebrates to large pelagic fish and marine mammals. Some seamounts are home to ancient coral gardens, deep water corals that grow slowly, live for centuries, and create complex three-dimensional habitats that support a dizzying array of species. And here is something truly extraordinary about seamounts. Because they are isolated from one another, each one a peak rising from the vast, flat abyssal plain, they often harbor endemic species, organisms found nowhere else on Earth. Each seamount can be thought of as an underwater island, and like islands on land, their isolation drives speciation. Scientists who study seamounts frequently discover new species, and many of these species are found on a single seamount and nowhere else. We are, in a very real sense, still discovering new worlds within our own ocean. Let us talk about salt. The ocean is salty, everyone knows that. But do you know how salty it is or where that salt comes from? The average salinity of the ocean is about 35 parts per thousand. That means that for every 1,000 grams of seawater, about 35 grams are dissolved salts. If you could extract all of the salt from the ocean and spread it evenly over the Earth's land surface, it would form a layer over 500 feet thick. That is a staggering amount of salt. The salt in the ocean comes from two primary sources. The first is the weathering of rocks on land. Rain, which is slightly acidic due to dissolved carbon dioxide, falls on land and slowly dissolves minerals from rocks and soil. Rivers carry these dissolved minerals to the ocean. Over millions and billions of years, this process has delivered an enormous quantity of dissolved salts to the sea. The second source is hydrothermal activity on the ocean floor. As seawater circulates through hot rock near mid-ocean ridges and hydrothermal vents, it dissolves minerals from the rock and carries them into the ocean. The salinity of the ocean is not uniform. It varies from place to place and from depth to depth. Near the equator, where rainfall is heavy, surface salinity tends to be lower. In subtropical regions, where evaporation is high and rainfall is low, surface salinity tends to be higher. In polar regions, the melting of ice can reduce salinity, while the formation of ice can increase it. These variations in salinity, combined with variations in temperature, drive the density differences that power thermohaline circulation, the great conveyor belt we discussed earlier. Everything in the ocean is connected. Temperature, salinity, density, circulation, they are all threads in a single, intricate tapestry. Here's another fact about the ocean that most people find surprising. The ocean has rivers, underwater rivers. In certain places, particularly in areas where dense, salty water flows along the ocean floor, you can find distinct channels of flowing water that look and behave much like rivers on land. One of the most famous underwater rivers was discovered in the Black Sea, where salty water from the Mediterranean flows along the seabed through a channel complete with banks, floodplains, and even rapids. If this underwater river were on the surface, it would be the sixth largest river in the world by volume. Similarly, the ocean has waterfalls. The Denmark Strait Cataract, located between Iceland and Greenland, is the largest known underwater waterfall on Earth. Cold, dense water from the Nordic seas plunges over a massive drop in the ocean floor, cascading downward for over 11,500 feet. That is more than 3 times the height of Angel Falls in Venezuela, the tallest waterfall on land. Yet because it occurs entirely beneath the ocean's surface, most people have never heard of it. The ocean has lakes too. On the ocean floor, in certain areas of the Gulf of Mexico and other regions, there are pools of super salty brine that are so much denser than the surrounding seawater that they form distinct pools with clearly defined shorelines. These brine pools sit on the ocean floor like lakes on land. They even have waves that lap at their edges. The brine in these pools is toxic to most marine life. The extreme salinity and the dissolved chemicals create an environment that kills most organisms on contact. Fish or crabs that wander into a brine pool often die within seconds. For this reason, these formations are sometimes called pools of death. Yet even here at the edges of these toxic lakes, specialized bacteria and other microorganisms have evolved to thrive, forming mats and communities that feed on the chemicals in the brine. Now, let us talk about one of the ocean's most awe-inspiring phenomena, waves and tsunamis. Ordinary ocean waves are generated by wind. The wind transfers energy to the surface of the water, creating ripples that grow into swells and eventually into the rolling waves that break on beaches around the world. The size of a wave depends on 3 factors: the speed of the wind, the duration of the wind, and the distance over which the wind blows, known as the fetch. The longest fetches are in the Southern Ocean, where winds can blow unimpeded around the entire circumference of the globe, with no landmasses to interrupt them. This is why the Southern Ocean is home to some of the largest and most powerful waves on Earth, with some reaching heights of over 60 feet during storms. But tsunamis are a different beast entirely. Unlike wind waves, which affect only the surface of the water, tsunamis are generated by the sudden displacement of an enormous volume of water, usually by an earthquake on the ocean floor, but sometimes by a volcanic eruption, a landslide, or even a meteorite impact. A tsunami is not a single wave but a series of waves, sometimes called a wave train. In the open ocean, a tsunami may have a wave height of only a few feet and a wavelength of hundreds of miles, making it virtually undetectable to ships at sea. The wave moves through the entire water column from surface to floor, traveling at speeds of up to 500 miles per hour, as fast as a commercial jet. But when a tsunami approaches shallow coastal waters, something dramatic happens. The front of the wave slows down as it encounters the rising ocean floor, while the back of the wave, still in deep water, continues at full speed. The wave compresses. The energy that was spread across a wavelength of hundreds of miles is squeezed into a space of just a few miles. The wave height increases dramatically, from a few feet to 30, 50, even 100 feet in extreme cases. The result is a wall of water that crashes onshore with almost unimaginable force, sweeping away everything in its path. The deadliest tsunami in recorded history struck on December 26, 2004, triggered by a magnitude 9.1 earthquake off the west coast of Sumatra. The tsunami radiated outward across the Indian Ocean, striking coastlines in 14 countries within hours. The waves reached heights of over 100 feet in some locations. More than 230,000 people were killed. Entire communities were erased. The energy released by the earthquake was equivalent to roughly 23,000 Hiroshima-type atomic bombs. It was a stark and devastating reminder of the ocean's power, a power that can, in a matter of minutes, reshape coastlines, destroy cities, and end hundreds of thousands of lives. The ocean also gives birth to some of the most powerful storms on the planet. Hurricanes, known as typhoons in the western Pacific and cyclones in the Indian Ocean, are fueled by warm ocean water. They are, in essence, massive heat engines. Warm, moist air rises from the ocean's surface, creating an area of low pressure. As more air rushes in to fill the void, the rotation of the Earth causes it to spiral, building the characteristic rotating structure of a tropical cyclone. The storm draws its energy from the warm water below, and as long as it remains over sufficiently warm water, it can continue to intensify. The strongest tropical cyclones can generate sustained winds of over 180 miles per hour and produce storm surges, walls of seawater pushed ashore by the wind, of over 20 feet. The destructive power of these storms is almost incomprehensible. A single hurricane can release as much energy as 10,000 nuclear weapons over the course of its lifetime. And as ocean temperatures rise, scientists warn that we may see more intense storms in the future, storms with higher wind speeds, heavier rainfall, and more destructive storm surges. But the ocean is not only a source of destruction. It is a source of life, a source of sustenance, a source of wonder. And one of the most wonderful things about the ocean is its sheer, breathtaking diversity of life. We have already spoken about coral reefs and deep-sea creatures, but the ocean's biodiversity extends far beyond these examples. Consider the octopus. Here is an animal that has 3 hearts, blue blood, and a brain so distributed that each of its 8 arms can taste, touch, and make decisions semi-independently. Octopuses are invertebrates. They have no bones, which means they can squeeze through openings barely larger than their eyeballs. They are masters of camouflage, able to change the color, pattern, and even texture of their skin in milliseconds to blend in with their surroundings or communicate with other octopuses. They have been observed using tools, stacking coconut shells to create shelters, for example. They can solve puzzles, open jars, and navigate mazes. Some species have been known to escape from aquarium tanks, cross the floor, enter other tanks to eat the fish inside, and then return to their own tanks before morning. The intelligence of octopuses is remarkable in part because it evolved independently from the intelligence of vertebrates. The last common ancestor of octopuses and humans lived over 500 million years ago. Whatever intelligence means to an octopus, it is a different kind of intelligence, forged by a completely different evolutionary path. In a sense, the octopus represents the closest thing we have found to alien intelligence right here on our own planet. And then there are the jellyfish. These ancient creatures have been drifting through the world's oceans for at least 500 million years, long before fish, long before the first animals crawled onto land. Jellyfish have no brain, no heart, no bones, no blood. They are approximately 95% water, and yet they are extraordinarily successful predators. Their tentacles are lined with specialized cells called cnidocytes, each containing a tiny coiled harpoon loaded with venom. When triggered, these harpoons fire in microseconds, one of the fastest mechanical processes in all of nature, injecting venom into prey or predators. Some jellyfish are enormous. The lion's mane jellyfish, found in cold northern waters, can have a bell diameter of over 6 feet and tentacles extending more than 100 feet, longer than a blue whale. Others are tiny but deadly. The box jellyfish, found in tropical waters of the Indo-Pacific, is widely considered the most venomous marine animal on Earth. Its venom attacks the heart, nervous system, and skin cells simultaneously, and a severe sting can kill a human in minutes. But perhaps the most astonishing jellyfish of all is Turritopsis doerner, commonly known as the immortal jellyfish. When this tiny species, barely 5 millimeters across, is injured, sick, or simply old, it can revert its cells to their earliest form and essentially restart its life cycle, transforming back into a juvenile polyp. In theory, this process can be repeated indefinitely, making Turritopsis doerner biologically immortal. It does not mean it cannot die, it can still be eaten or killed by disease, but in terms of aging, it has found a loophole. Scientists are studying this process intensely, hoping it may one day yield insights into human aging and disease. Let us turn now to the relationship between the ocean and climate, because this relationship is one of the most important dynamics on our planet. We have already discussed how the ocean absorbs heat and carbon dioxide. But the ocean also plays a critical role in the water cycle, which drives weather patterns around the globe. Every day, the sun's energy causes enormous quantities of water to evaporate from the ocean's surface. This water vapor rises into the atmosphere, forms clouds, and eventually falls as precipitation, rain, snow, sleet, or hail. Most of this precipitation falls back into the ocean, but a significant portion falls on land, replenishing rivers, lakes, groundwater, and reservoirs. Without the ocean, there would be no water cycle. Without the water cycle, there would be no fresh water. Without fresh water, there would be no terrestrial life as we know it. The ocean is, quite literally, the source of every glass of water you have ever drunk, every rainstorm you have ever witnessed, every snowflake that has ever fallen. The ocean also influences weather patterns through large-scale climate phenomena like El Niño and La Niña. These are periodic changes in the temperature of the surface waters of the tropical Pacific Ocean that have far-reaching effects on weather patterns around the world. During an El Niño event, the surface waters of the central and eastern Pacific warm significantly. This warming alters atmospheric circulation patterns, leading to changes in rainfall and temperature across the globe. Some regions experience drought while others are inundated with flooding. Weather patterns that normally operate with clockwork regularity are disrupted, sometimes catastrophically. La Niña is essentially the opposite, a cooling of the same Pacific surface waters, which produces its own set of global weather impacts. Together, El Niño and La Niña are part of a larger pattern called the El Niño Southern Oscillation, or ENSO, and understanding this pattern is critical for predicting weather, managing agriculture, and preparing for natural disasters. The ocean, through ENSO and other mechanisms, reaches far inland, shaping the lives of people who may never see the sea. Let us now consider something that most people take completely for granted: the tides. Twice each day in most parts of the world, the ocean rises and falls in a rhythm as predictable as clockwork. High tide, low tide, high tide, low tide. This ceaseless oscillation is driven primarily by the gravitational pull of the moon, with a smaller contribution from the sun. The moon's gravity pulls on the Earth's water, creating a bulge of water on the side of the Earth facing the moon. At the same time, inertia creates a second bulge on the opposite side of the Earth. As the Earth rotates, different locations pass through these bulges, experiencing high tides. The height of the tides varies enormously depending on geography. In the open ocean, the tidal range, the difference between high and low tide, is typically only about a foot or two. But in certain coastal areas, the shape of the coastline and the ocean floor can amplify tides dramatically. The Bay of Fundy, located between the provinces of Nova Scotia and New Brunswick in Canada, has the highest tides in the world. The tidal range in the Bay of Fundy can exceed 50 feet. That means the difference between high and low tide is equivalent to a 5-story building. When the tide comes in, it brings approximately 100 billion tons of water into the bay. When it goes out, it drains that same amount, twice a day, every day. Tides are not just a curiosity, they are ecologically critical. The intertidal zone, the area between the high tide line and the low tide line, is one of the most dynamic and challenging habitats on Earth. Organisms living in this zone must cope with constant change, submerged in salt water for part of the day, exposed to air and sunlight for the rest. pounded by waves, baked by the sun, frozen in winter, flooded by rain. The creatures that thrive here, barnacles, mussels, sea stars, crabs, sea anemones, various species of algae, are among the toughest and most adaptable organisms on the planet. There is another ocean phenomenon that deserves our attention, the Great Pacific Garbage Patch. Located in the central North Pacific Ocean, this is the largest accumulation of ocean plastic in the world, but if you were to sail through it, you might be surprised. The garbage patch is not a solid island of trash, as many people imagine. Most of the debris consists of microplastics, tiny fragments of plastic less than 5 millimeters in size, suspended in the water column like a diffuse soup. The patch covers an estimated area of roughly 600,000 square miles, more than twice the size of Texas. Some estimates put it even larger. The plastic in the garbage patch comes from everywhere. It enters the ocean from rivers, coastlines, fishing boats, and ships. Once in the ocean, it is carried by currents into large rotating current systems called gyres. The North Pacific Subtropical Gyre, a system of circular ocean currents, traps the plastic and concentrates it in a broad zone. The plastic does not biodegrade in any meaningful time frame. Instead, it breaks down into smaller and smaller pieces through the action of sunlight and wave energy. These microplastics are ingested by marine organisms at every level of the food chain, from tiny zooplankton to large fish and seabirds. The chemicals associated with plastics can accumulate in the tissues of these organisms, with potential effects that scientists are still working to understand. The ocean is not just one garbage patch, though. There are 5 major oceanic gyres, and each one has its own accumulation zone. Plastic pollution is a truly global problem, affecting every ocean, every coastline, and potentially every marine organism on the planet. An estimated 8 million metric tons of plastic enter the ocean every year. If current trends continue, some scientists project that by the middle of this century, there could be more plastic in the ocean by weight than fish. And yet, even in the face of these challenges, the ocean continues to astound us with its beauty, its complexity, and its capacity to surprise. New species are discovered in the ocean every year, sometimes hundreds of them. In recent deep-sea expeditions, scientists have encountered creatures so unusual, so unexpected that they struggle to classify them. Transparent fish with visible organs, worms that live inside whale bones and digest them using symbiotic bacteria. Sponges made of glass, sea cucumbers that can liquefy their own bodies to escape through narrow cracks. The ocean is an engine of evolution, constantly producing new forms of life, new adaptations, new solutions to the challenges of survival. There's a region of the ocean that scientists call the oxygen minimum zone. At certain depths, typically between about 600 and 3,300 feet, the concentration of dissolved oxygen drops to extremely low levels. These zones occur because the oxygen consumed by bacteria decomposing sinking organic matter is not replenished by photosynthesis, which requires sunlight and occurs only near the surface, or by mixing with oxygen-rich surface waters. In severe cases, these zones can become so depleted of oxygen that they are essentially dead zones, hostile to most forms of life. Climate change is expanding these oxygen minimum zones, as warmer water holds less dissolved oxygen and increased stratification reduces the mixing that brings oxygen to deeper layers. The expansion of oxygen minimum zones is a growing concern, as it reduces the habitable space available to many marine species and can force them into shallower, warmer waters where they may face additional stresses. Let us also consider the ocean's role in human history and culture. The ocean has shaped the course of civilization in ways both obvious and subtle. It has been a highway for exploration, trade, and migration. The Polynesians crossed thousands of miles of open Pacific in outrigger canoes, navigating by the stars, the currents, and the behavior of seabirds, in one of the most remarkable feats of navigation in human history. The Vikings crossed the North Atlantic to reach Iceland, Greenland, and eventually North America centuries before Columbus. The great maritime empires of Portugal, Spain, the Netherlands, and Britain were built on their ability to traverse the ocean, connecting continents and reshaping the political and cultural geography of the world. The ocean has also been a source of sustenance for as long as humans have existed. Coastal communities around the world have depended on the ocean for food since the earliest days of our species. Fish, shellfish, seaweed, sea mammals, the ocean has fed billions of people over thousands of generations. Today, the global fishing industry supplies a significant portion of the protein consumed by the human population. Over 3 billion people depend on the ocean as their primary source of protein, but the ocean's capacity to provide is not infinite. Overfishing has pushed many fish stocks to dangerous levels. According to the United Nations Food and Agriculture Organization, approximately one-third of the world's fish stocks are overfished, harvested at levels that are biologically unsustainable. Another 60% are fished at their maximum sustainable yield, leaving almost no room for increased harvesting. The decline of fish stocks has consequences that extend far beyond the fishing industry. It affects the livelihoods of millions of small-scale fishers around the world, the food security of entire nations, and the health of marine ecosystems that depend on balanced predator-prey relationships. Deep-sea trawling, the practice of dragging heavy nets across the ocean floor, is particularly destructive. The nets crush and destroy everything in their path: corals, sponges, sea fans, and the countless organisms that live among them. Scientists have compared the impact of deep-sea trawling to clear-cutting a forest, except that the deep-sea ecosystems destroyed by trawling may take centuries or even millennia to recover, if they recover at all. The slow growth rates and low reproduction rates of many deep-sea species make them especially vulnerable to this kind of disturbance. The ocean also holds vast mineral resources. The ocean floor is dotted with polymetallic nodules, potato-sized lumps of metal that contain manganese, nickel, cobalt, copper, and rare earth elements. These nodules form over millions of years as minerals precipitate from seawater around a small nucleus, a shark tooth, a fragment of shell. The nodule fields of the Clarion-Clipperton Zone in the Central Pacific are estimated to contain more nickel, manganese, and cobalt than all known terrestrial reserves combined. As demand for these metals grows, driven in part by the production of batteries for electric vehicles and electronics, interest in deep-sea mining has intensified, but deep-sea mining is profoundly controversial. The ecosystems of the abyssal plain, while they may appear barren, are in fact home to diverse communities of organisms, many of which are new to science. Removing nodules from the ocean floor disturbs the sediment, destroys habitat, and creates plumes of fine particles that can spread for miles, potentially smothering filter-feeding organisms and disrupting food webs. The environmental impacts of deep-sea mining are poorly understood, and many scientists have called for a moratorium on mining activities until more research can be conducted. As we approach the midpoint of our exploration, let us pause for a moment and reflect on something fundamental. The ocean is not just a body of water. It is a living system, a complex, dynamic, interconnected web of physical, chemical, and biological processes that sustains life on this planet. It regulates our climate, it produces our oxygen, it feeds our communities, it inspires our imaginations, it humbles our ambitions. Every breath we take, every drop of rain that falls, every meal that includes seafood, every moderate temperature we enjoy, all of it is a gift from the ocean. And the ocean is in trouble. Warming, acidification, pollution, overfishing, habitat destruction, the threats are real, they are serious, and they are accelerating. But the ocean is also resilient. When given the chance, marine ecosystems can recover with remarkable speed. Marine protected areas, regions of the ocean where human activities are restricted or prohibited, have shown that fish populations can rebound, coral can regrow, and biodiversity can flourish when the pressures are removed. The ocean has been through catastrophes before: mass extinctions, asteroid impacts, ice ages. It has always recovered. The question is not whether the ocean will survive. It will. The question is whether it will survive in a form that can continue to support us. That is the question that should keep us all awake at night, and that is the question we will continue to explore. The ocean hides not only biological wonders but also an immense archive of human history. The seafloor is the world's largest museum, holding within its sediments and upon its rocky outcrops the remnants of thousands of years of human civilization. There are more shipwrecks on the ocean floor than there are artifacts in all the world's museums combined. Estimates suggest that there are over 3 million shipwrecks lying on the ocean floor around the world, spanning every era of maritime history, from ancient Phoenician trading vessels to World War II battleships, from Spanish galleons laden with gold to humble fishing boats lost in sudden storms. Some of these wrecks have become legendary. The Titanic, perhaps the most famous shipwreck of all time, lies more than 12,500 feet below the surface of the North Atlantic, broken in two pieces and slowly being consumed by iron-eating bacteria. Scientists estimate that the wreck will be completely gone within a few more decades, dissolved and consumed by the very ocean that claimed it. The Titanic is not just a ship. It is a monument to human ambition and human fallibility, and its resting place 2.5 miles below the waves, in the perpetual darkness and near freezing cold of the deep Atlantic, is a reminder that the ocean does not care about human hubris. It takes what it takes and gives back nothing. Other wrecks tell different stories. The ancient Antikythera wreck, discovered off the coast of a small Greek island, yielded one of the most astonishing archaeological finds in history. The Antikythera mechanism, a complex mechanical device dating to around 100 BC. This device, often described as the world's first analog computer, was used to predict astronomical positions and eclipses. Its discovery on the ocean floor forced historians to radically revise their understanding of the technological capabilities of the ancient world. Without the ocean's preserving embrace, cold, dark, low in oxygen, this device would have been lost to corrosion and decay long ago. The ocean preserves not only human artifacts, but also the geological and biological record of the planet itself. Layers of sediment on the ocean floor contain a detailed archive of Earth's climate history, stretching back millions of years. By drilling into these sediments and analyzing their composition, the types of fossils they contain, the ratios of certain isotopes, the presence of specific minerals, scientists can reconstruct past temperatures, ocean currents, atmospheric composition, and even the timing of major geological events. Much of what we know about past ice ages, past warm periods, and the long-term evolution of Earth's climate comes from these deep-sea sediment cores. The ocean floor is, in a very real sense, the planet's memory. There is a substance on the ocean floor that has the potential to transform global energy supply or trigger catastrophic climate change. Methane hydrate, also known as methane clathrate, is a crystalline solid in which molecules of methane gas are trapped within a cage of water ice molecules. These deposits are found in vast quantities beneath the ocean floor, particularly along continental margins where the pressure is high and the temperature is low. The amount of energy locked up in methane hydrate deposits is estimated to exceed the combined energy content of all known reserves of coal, oil, and natural gas. But methane hydrate is also profoundly dangerous. Methane is a potent greenhouse gas, roughly 80 times more effective at trapping heat than carbon dioxide over a 20-year period. If ocean temperatures rise enough to destabilize methane hydrate deposits, the released methane could enter the atmosphere and accelerate warming in a feedback loop that some scientists have termed the clathrate gun hypothesis. While most scientists consider a sudden, catastrophic release of methane from hydrates unlikely, the possibility cannot be entirely ruled out, and even a gradual release could significantly amplify the effects of climate change. Let us travel now to one of the most productive and vital regions of the ocean, the coastal zone. The coastal zone, where the land meets the sea, is one of the most densely populated and economically important areas on the planet. An estimated 40% of the world's population lives within 60 miles of the coast. Coastal cities are hubs of trade, industry, culture, and innovation. And yet, the coastal zone is also one of the most vulnerable areas on Earth, exposed to rising seas, intensifying storms, erosion, and the increasing pressures of human development. Within the coastal zone, there are ecosystems of extraordinary importance. Mangrove forests line tropical and subtropical coastlines around the world, forming dense thickets of salt-tolerant trees that grow in the boundary between land and sea. Mangroves are ecological powerhouses. Their tangled root systems provide critical habitat for juvenile fish, shrimp, crabs, and countless other species. Many commercially important fish species spend part of their life cycle in mangrove nurseries. Mangroves also protect coastlines from erosion and storm damage, absorbing the energy of waves and storm surges far more effectively than any human-engineered seawall. And they are prolific carbon sinks, storing up to 4 times more carbon per unit area than terrestrial tropical forests. Despite their immense value, mangrove forests are disappearing at an alarming rate. Over the past 50 years, an estimated 35% of the world's mangroves have been lost, cleared for coastal development, aquaculture ponds, and agriculture. The loss of mangroves has cascading effects: increased coastal erosion, reduced fish populations, diminished storm protection, and the release of stored carbon back into the atmosphere. Seagrass meadows are another coastal ecosystem of critical importance. These underwater grasslands, found in shallow coastal waters around the world, are among the most productive ecosystems on the planet. A single acre of seagrass can produce over 10 tons of leaves per year, providing food and habitat for a wide range of species, including sea turtles, manatees, dugongs, seahorses, and countless species of fish and invertebrates. Seagrasses also play a vital role in carbon storage, capturing carbon dioxide from the water and sequestering it in their roots and the surrounding sediment. Per unit area, seagrass meadows can sequester carbon up to 35 times faster than tropical rainforests. Like mangroves, seagrass meadows are declining. An estimated 7% of the world's seagrass habitat is lost each year due to coastal development, pollution, dredging, and damage from boat anchors and propellers. The loss of seagrass meadows represents not only a loss of habitat and biodiversity, but also a loss of one of nature's most effective carbon capture systems. Salt marshes round out the trio of critical coastal ecosystems. Found primarily in temperate and high-latitude regions, salt marshes are flat, muddy areas that are regularly flooded by tides and dominated by salt-tolerant grasses and other plants. Like mangroves and seagrasses, salt marshes provide essential habitat for fish and wildlife, protect coastlines from erosion and storm damage, filter pollutants from water, and store significant amounts of carbon. And like mangroves and seagrasses, salt marshes are in decline, lost to development, drainage, and pollution. The interconnection of these coastal ecosystems is profound. A juvenile fish might be born on a coral reef, migrate to a mangrove forest to grow and feed, spend time in a seagrass meadow, and eventually move to deeper waters as an adult. Remove any one of these habitats and the entire chain is broken. The health of the ocean depends not on any single ecosystem in isolation, but on the connections between them. As we draw this first part of our documentary to a close, let us consider one more thing: sound. The ocean is not a silent world. It is, in fact, a world of sound. Sound travels approximately 4.5 times faster in water than in air, and it travels much farther. Marine mammals, whales, dolphins, seals depend on sound for communication, navigation, and hunting. The songs of humpback whales are among the most complex and haunting sounds in the animal kingdom. These songs can last for hours and are composed of distinct phrases and themes that evolve over time. All males in a given population sing the same song, but the song changes from year to year, with new elements being introduced and old elements being dropped. The songs spread between populations, suggesting a form of cultural transmission that is still not fully understood. But the ocean's soundscape is changing. Human activities, shipping, sonar, oil and gas exploration, construction, have dramatically increased the level of noise in the ocean. The noise from a single large container ship can be detected from hundreds of miles away. Military sonar can produce sounds exceeding 230 decibels, loud enough to cause physical injury to nearby marine mammals. The cumulative effect of this noise pollution is profound. It can interfere with the ability of whales and dolphins to communicate, navigate, find food, and avoid predators. It can cause chronic stress, behavioral changes, and in some cases, physical harm. Strandings of beaked whales and other deep-diving species have been linked to naval sonar exercises. The ocean is becoming louder, and the creatures that depend on sound are paying the price. The ocean is a world of paradoxes. It is vast, yet fragile. It is powerful, yet vulnerable. It sustains us, yet we take it for granted. It holds the keys to our past, our present, and our future. It is the last great frontier of exploration, the greatest reservoir of biodiversity on Earth, and the single most important factor in the regulation of our planet's climate. And it is changing faster than at any point in human history. Let us begin with a journey that has been happening for over 100 million years, a journey so extraordinary, so precisely calibrated, that scientists are still struggling to fully explain it. The migration of the sea turtle. Sea turtles are among the most ancient creatures in the ocean. They have been swimming these waters since the age of the dinosaurs, and in all that time, their fundamental behavior has changed remarkably little. 7 species of sea turtles exist today, and all of them are migratory. Some species travel thousands of miles between their feeding grounds and their nesting beaches. The leatherback sea turtle, the largest of all sea turtles, capable of reaching over 6 feet in length and weighing more than 1,000 pounds, makes some of the longest migrations of any marine animal, crossing entire ocean basins to reach the beaches where they were born. And that is the most remarkable part. Sea turtles return to the same beach where they hatched, sometimes decades after leaving it, as tiny hatchlings no bigger than the palm of your hand. A female leatherback might spend 20 or 30 years roaming the open ocean, traveling tens of thousands of miles, and then, when she is ready to lay her eggs, she will navigate back to the exact stretch of sand where she first crawled out of her own egg and made her way to the sea. How does she do it? How does an animal with a brain the size of a walnut navigate across featureless expanses of open ocean to find a specific beach on a specific coastline, potentially on the other side of the world? The answer, scientists now believe, lies in the Earth's magnetic field. Sea turtles can detect the strength and angle of the planet's magnetic field, and they use this information as a kind of internal GPS system. Each location on Earth has a unique magnetic signature, a specific combination of field intensity and inclination angle, and sea turtles appear to imprint on the magnetic signature of their natal beach at the moment of hatching. They carry this magnetic map with them for their entire lives, and when the time comes to nest, they follow it home. This magnetic sense is not unique to sea turtles. Many marine species are believed to use the Earth's magnetic field for navigation, including certain species of sharks, rays, salmon, and lobsters. But sea turtles are perhaps the most dramatic example because their migrations are so long, so precise, and so faithful. A turtle that was born on a beach in the western Atlantic might feed in waters off the coast of West Africa, then cross the entire ocean to return to the same beach, sometimes the same few hundred meters of beach, to lay her eggs. The precision is almost unbelievable, and it has been happening generation after generation for 100 million years, but sea turtles face a gauntlet of threats. Their nesting beaches are being developed, eroded, and illuminated by artificial light, which disorients hatchlings, who instinctively crawl toward the brightest horizon, which in a natural setting would be the ocean reflecting moonlight, but in a developed setting might be a parking lot or a highway. Plastic pollution is a major killer. Sea turtles frequently mistake floating plastic bags for jellyfish, one of their primary food sources. Ingesting plastic can block their digestive tracts and lead to starvation. Fishing gear entangles and drowns thousands of sea turtles every year. and rising temperatures pose a unique threat to sea turtle reproduction because the sex of a sea turtle is determined not by genetics but by the temperature of the sand in which the egg develops. Warmer sand produces females, cooler sand produces males. As global temperatures rise, some nesting beaches are producing almost exclusively female hatchlings. If this trend continues, entire populations could face a critical shortage of males, threatening their ability to reproduce. 6 of the 7 species of sea turtles are currently classified as threatened or endangered. These are animals that survived the asteroid that killed the dinosaurs. They survived ice ages. They survived millions of years of predation, competition, and environmental change. And now, in the span of a few human generations, we have pushed them to the edge. From creatures that navigate by magnetism, let us turn to a place where navigation becomes a matter of life and death: underwater caves. The ocean is riddled with them. Along coastlines around the world, geological processes have carved elaborate cave systems that extend deep into the rock, sometimes stretching for miles, sometimes descending hundreds of feet below the surface. These caves are among the most dangerous environments on Earth for human exploration, and also among the most scientifically valuable. Underwater caves, particularly those found in limestone karst regions, are formed over thousands to millions of years by the slow dissolution of rock by slightly acidic water. As the rock dissolves, it creates tunnels, chambers, and passageways of extraordinary complexity. Some of these caves are flooded with fresh water, others are flooded with seawater, and in some cases a freshwater layer sits on top of a saltwater layer, creating a visible boundary called a halocline, a shimmering, wavy interface where the two water masses meet but do not mix, creating an eerie visual effect that has been described as looking like an underwater mirage. The caves of the Yucatan Peninsula are among the most famous and most extensive underwater cave systems in the world. Known locally as cenotes, these natural sinkholes provide access to a vast network of submerged passages that extend for hundreds of miles beneath the jungle floor. The ancient Maya considered cenotes sacred portals to the underworld, and archaeological explorations of these caves have yielded extraordinary discoveries, including human remains, pottery, jade artifacts, and evidence of ritual sacrifice dating back thousands of years. The cold, oxygen-poor water of the cenotes preserves organic materials remarkably well, providing archaeologists with a window into the past that is unmatched by most terrestrial sites. But the caves hold even older secrets. In several cenotes, the remains of Pleistocene megafauna have been discovered, the bones of giant ground sloths, saber-toothed cats, and other animals that lived during the last ice age, when sea levels were much lower and the caves were dry. These fossils provide crucial data about the ecosystems of the deep past and help scientists understand how species responded to the dramatic climate changes that accompanied the advance and retreat of continental ice sheets. Cave diving, the exploration of these submerged passages, is one of the most hazardous activities in the world. The passages can be narrow, disorienting, and labyrinthine. Visibility can drop to 0 in seconds if a diver's movements stir up fine sediment from the floor. There is no surface to swim to in an emergency. The only way out is back through the passages you came in. Every year, divers die in underwater caves, and the community of cave divers is acutely aware of the risks. Yet they continue to explore, driven by the knowledge that these caves contain discoveries, geological, biological, archaeological, that cannot be found anywhere else. One of the most fascinating biological discoveries in underwater caves involves organisms that have been isolated from the outside world for millions of years. In some caves, particularly those that have been sealed off from the surface for extended periods, scientists have found communities of organisms that have evolved in complete independence from the rest of the biosphere. These creatures are often eyeless, colorless, and exquisitely adapted to life in total darkness. Some feed on bacteria that derive energy from chemical reactions rather than sunlight, chemosynthetic ecosystems similar in principle to those found around deep-sea hydrothermal vents. These cave ecosystems are living laboratories of evolution, demonstrating how life adapts to extreme conditions and how isolation drives speciation. Speaking of extreme survival, let us meet an organism that takes toughness to an entirely different level, the tardigrade. Also known as water bears or moss piglets, tardigrades are microscopic animals, typically less than a millimeter in length, that are found in virtually every environment on Earth, including the ocean. They live in deep-sea sediments, on coral reefs, in intertidal zones, and even in the water column itself. But what makes tardigrades truly extraordinary is not where they live, but what they can survive. Tardigrades can survive temperatures as low as -458 degrees Fahrenheit, just above absolute zero, and as high as 300 degrees Fahrenheit. They can survive pressures 6 times greater than those found in the deepest ocean trenches. They can survive radiation doses hundreds of times greater than the lethal dose for a human. They can survive the vacuum of outer space. And they can survive complete desiccation, being dried out to the point where their bodies contain virtually no water for decades, possibly centuries. When exposed to extreme conditions, tardigrades enter a state called cryptobiosis, in which their metabolism drops to nearly zero. They curl into a tiny ball called a tun, replace the water in their cells with a sugar called trehalose, which forms a protective glass-like matrix and essentially shut down. When conditions improve, when water returns, when temperature normalizes, they revive and carry on as if nothing happened. Tardigrades have been sent into space and exposed to the full fury of cosmic radiation and vacuum. They survived. They have been frozen in Antarctic ice for decades and revived. They have been found in hot springs, in the sediments of the deepest ocean, and in the thin films of water on mosses growing on mountain tops. They are, by any measure, the most resilient animals on Earth, and the ocean is full of them. Marine tardigrades crawl through the spaces between grains of sand on the seafloor, feeding on bacteria and algae, virtually invisible and virtually indestructible. While tardigrades represent the pinnacle of microscopic toughness, the ocean is also home to organisms that achieve remarkable feats on a much larger scale. Consider the Arctic jellyfish known as the lion's mane, which we mentioned briefly earlier. But now consider the depths of the Arctic and Antarctic oceans, where conditions are so extreme that the organisms living there have evolved some truly extraordinary adaptations. Antarctic icefish, for example, are the only known vertebrates that lack red blood cells and hemoglobin, the protein that carries oxygen in the blood of virtually every other vertebrate on Earth. Their blood is transparent. Instead of relying on hemoglobin to transport oxygen, icefish absorb oxygen directly through their skin and gills, aided by the fact that cold water holds more dissolved oxygen than warm water. Their blood contains natural antifreeze proteins that prevent ice crystals from forming in their tissues. These adaptations allow icefish to thrive in waters that would kill most other fish within minutes. Antifreeze proteins are not unique to icefish. Many polar marine organisms, including certain species of fish, insects, and plants, produce antifreeze compounds that lower the freezing point of their body fluids. These proteins work not by lowering the freezing point in the way that salt lowers the freezing point of water on a road, but by binding to tiny ice crystals and preventing them from growing. The ice crystals are stopped in their tracks, unable to expand and rupture cells. This is molecular engineering of the highest order, and scientists are actively studying these proteins for potential applications in medicine, food preservation, and cryogenics. Now let us talk about one of the ocean's most extraordinary and least known phenomena, the whale fall. When a whale dies in the open ocean, its massive body sinks to the seafloor. This event, a whale fall, creates an ecosystem that can persist for decades. A single whale carcass can weigh tens of tons and contains an enormous amount of organic material, blubber, muscle, bone, oil. In the nutrient-poor environment of the deep sea, a whale fall is a bonanza, a sudden, overwhelming windfall of food. The colonization of a whale fall proceeds in stages. First come the mobile scavengers, hagfish, sleeper sharks, crabs, and amphipods, which can strip the soft tissue from a whale carcass in a matter of months. Hagfish, those ancient, jawless, eel-like creatures that tie themselves in knots and produce copious quantities of slime, are often the first to arrive. They bore into the carcass, consuming it from the inside out. A single whale fall can attract hundreds of hagfish, along with dozens of other scavenger species. After the soft tissue is gone, a second community takes over. These are the enrichment opportunists, worms, crustaceans, and other organisms that feed on the organic rich sediment surrounding the carcass. The oils and fats that leached from the whale's body into the surrounding seafloor create a nutrient-rich zone that can support dense communities of these organisms for years. The final stage is the most remarkable. The whale's skeleton, rich in lipids stored within the bones, becomes a home for chemosynthetic bacteria. These bacteria break down the lipids and produce hydrogen sulfide, the same compound that fuels hydrothermal vent communities. The whale bones become, in effect, miniature hydrothermal vents, supporting communities of organisms that include specialized bone-eating worms called ostacs. These worms have no mouth, no stomach, and no digestive system. Instead, they bore into the whale bone using root-like structures and rely on symbiotic bacteria within their tissues to break down the bone's lipids and extract nutrients. A single whale fall can support a thriving community for 50 to 100 years. Scientists have discovered more than 400 species associated with whale falls, and many of these species are found nowhere else. Whale falls may serve as stepping stones for deep-sea organisms, connecting the widely scattered oases of hydrothermal vents and cold seeps and allowing species to disperse across the vast, barren expanses of the abyssal plain. The death of a whale is not an ending. It is a beginning, the birth of an entire ecosystem. Let us now explore one of the most enigmatic regions of the ocean, the Sargasso Sea. Unlike every other sea on Earth, the Sargasso Sea has no coastline. It is defined not by land but by ocean currents. Located in the North Atlantic, it is bounded by four major currents: the Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south. These currents circulate clockwise around a vast area of relatively calm, warm water that sits like an eye in the center of a slowly rotating gyre. The Sargasso Sea gets its name from sargassum, a genus of free-floating brown seaweed that accumulates in enormous quantities on its surface. Mats of sargassum can stretch for miles, creating a floating habitat that supports a unique community of organisms. Sargassum fish, small, mottled, and almost perfectly camouflaged to blend in with the seaweed, lurk among the fronds, ambushing prey. Juvenile sea turtles shelter in the sargassum mats, feeding and growing in relative safety. Shrimp, crabs, nudibranchs, and dozens of other species live their entire lives within this floating jungle. But the Sargasso Sea's greatest mystery involves the European and the related species of eel. For centuries, the life cycle of eels baffled naturalists. Eels were common in rivers and lakes across Europe and eastern coastal regions, but no one had ever found an eel egg or observed eels mating. Where did they come from? The ancient Greeks believed eels arose spontaneously from mud. Aristotle himself pondered the question and could not find an answer. The mystery was not solved until the early 20th century, when a Danish biologist named Johannes Schmidt spent nearly 2 decades trawling the Atlantic Ocean, collecting progressively smaller eel larvae and tracing them back toward their point of origin. His conclusion was astonishing. All European eels, every single one found in every river, lake, and stream from Scandinavia to North Africa, were born in the Sargasso Sea. Adult eels, when the time comes to reproduce, leave their freshwater habitats, travel downstream to the ocean, and then swim thousands of miles across the Atlantic to the Sargasso Sea, where they spawn, lay their eggs, and die. The larvae, called leptosphali, tiny, transparent, leaf-shaped creatures, drift on ocean currents for 1 to 3 years, slowly making their way back across the Atlantic to the rivers and streams their parents left. It is one of the most epic and mysterious migrations in the animal kingdom, and despite decades of research, no one has ever observed eels mating in the wild. The spawning grounds of the eel remain, to this day, one of the ocean's deepest secrets. Now, let us discuss an area of the ocean that is vital to human well-being in ways that most people never consider: the ocean's role in medicine. The sea is increasingly being recognized as one of the most promising frontiers in pharmaceutical research. Marine organisms produce an extraordinary array of chemical compounds, toxins, pigments, structural molecules, signaling chemicals, many of which have no analog in terrestrial organisms. These compounds have evolved over hundreds of millions of years in response to the unique pressures of the marine environment, and they represent a vast, largely untapped library of potential drugs. Several important medicines have already been derived from marine organisms. Ziconotide, a powerful painkiller used to treat severe chronic pain, was developed from a toxin produced by a cone snail, a marine snail that hunts fish by firing venomous harpoons from a modified tooth. The venom of cone snails is a complex cocktail of hundreds of different peptides, each targeting specific receptors in the nervous system. Scientists have barely begun to catalog the compounds found in cone snail venom, and each species produces a unique set of toxins. There are over 700 known species of cone snails, and their venoms are a treasure trove for drug discovery. RSC, a chemotherapy drug used to treat leukemia and lymphoma, was developed from compounds originally isolated from a Caribbean sea sponge. Traptidin, another cancer drug, was derived from a compound produced by a sea squirt, a filter-feeding marine invertebrate that looks nothing like a source of life-saving medicine. Eribulin, used to treat metastatic breast cancer, was inspired by a compound from a marine sponge found in the waters off Japan. Beyond specific drugs, marine organisms have contributed to breakthroughs in biotechnology and biomedical research. The green fluorescent protein, or GFP, originally isolated from a species of jellyfish, has become one of the most important tools in modern biology. By attaching GFP to other proteins, scientists can make those proteins glow, allowing them to track biological processes in living cells with unprecedented precision. The discovery and development of GFP earned its researchers the Nobel Prize in Chemistry, and it all started with a glowing jellyfish. The ocean's potential contributions to medicine are almost certainly far greater than what has been discovered so far. With millions of marine species still undescribed, and with the vast majority of marine chemical compounds still uncharacterized, the ocean represents a pharmaceutical frontier of almost limitless potential. But this potential is threatened by the same forces that threaten the ocean itself: pollution, habitat destruction, climate change, and the loss of biodiversity. Every species that goes extinct before it is studied is a library burned before it is read. Let us shift our focus now to energy. The ocean is not only a source of biological and chemical resources, it is also a source of energy, vast, renewable, and largely untapped. The energy contained in the ocean's waves, tides, currents, and thermal gradients is enormous. Scientists estimate that the global potential for ocean energy could supply a significant portion of the world's electricity needs if the technology to harness it can be made practical and affordable. Wave energy converters capture the kinetic energy of ocean waves and convert it into electricity. Tidal energy systems use the rise and fall of the tides to drive turbines, much as hydroelectric dams use the flow of rivers. Ocean thermal energy conversion, or OTEC, exploits the temperature difference between warm surface water and cold deep water to generate electricity through a heat exchange process. Each of these technologies faces significant engineering challenges. The marine environment is harsh, corrosive, and unpredictable, but progress is being made. Offshore wind energy, while technically harnessing the wind rather than the ocean itself, represents another rapidly growing source of renewable energy. Wind speeds over the ocean are generally higher and more consistent than over land, making offshore wind farms highly productive. Floating wind turbines, which can be deployed in deep water far from shore, are expanding the potential for offshore wind energy into areas that were previously inaccessible. The ocean's energy potential is not limited to renewables. As we discussed in the first part of this documentary, the ocean floor contains vast reserves of methane hydrate as well as conventional oil and gas deposits. Offshore drilling has been a major source of fossil fuel production for decades, but it carries significant environmental risks, as demonstrated by catastrophic spills that have devastated marine ecosystems and coastal communities. The challenge of the coming decades will be to transition from fossil fuel extraction to renewable ocean energy in a way that minimizes environmental harm and maximizes the benefits to human society. Now, let us meet one of the ocean's most visually spectacular and intellectually fascinating inhabitants, the cuttlefish. Related to octopuses and squid, cuttlefish are cephalopods, a group of mollusks that includes some of the most intelligent invertebrates on the planet. Cuttlefish have a remarkable ability to change the color, pattern, and texture of their skin almost instantaneously. Their skin contains millions of specialized cells called chromatophores, each filled with pigment and surrounded by tiny muscles. By expanding or contracting these muscles, the cuttlefish can create an astonishing range of visual displays, rippling waves of color, pulsating patterns, flashes of iridescence. They can match the color and texture of virtually any background, becoming invisible against sand, rock, coral, or seaweed in a fraction of a second. But cuttlefish do not just use their color-changing abilities for camouflage. They also use them for communication. Male cuttlefish engage in elaborate visual displays to attract mates and intimidate rivals. A male might display aggressive, high-contrast patterns on the side of his body facing a rival, while simultaneously displaying soft, female-mimicking patterns on the side facing a potential mate, essentially running two different visual conversations at the same time. Some smaller males have been observed mimicking the appearance of females in order to sneak past larger, dominant males and mate without being detected. It is a level of visual deception and social manipulation that is breathtaking in its sophistication. Cuttlefish also possess remarkable cognitive abilities. They can learn from observation, solve problems, and exhibit what appears to be a form of episodic memory, the ability to remember specific events from the past, including what happened, where it happened, and when it happened. This type of memory was long thought to be unique to humans and perhaps a few other vertebrates. Finding it in a mollusk, an animal whose lineage diverged from ours over 500 million years ago, has profound implications for our understanding of the evolution of intelligence. And then there is the mantis shrimp. Despite its name, it is neither a mantis nor a shrimp. It is a stomatopod, a crustacean with a lineage stretching back over 400 million years. Mantis shrimp are relatively small, typically ranging from a few inches to about a foot in length, but they are among the most formidable predators, pound for pound, in the ocean. There are two main types of mantis shrimp, classified by their weapons. Smashers have club-like appendages that they use to bludgeon their prey with devastating force. The strike of a smasher mantis shrimp is one of the fastest movements in the animal kingdom, accelerating at over 10,000 times the force of gravity and reaching speeds of over 50 miles per hour. The strike is so fast and so powerful that it creates cavitation bubbles in the water, tiny pockets of vacuum that collapse with enough force to produce a secondary shock wave, a flash of light, and temperatures briefly reaching thousands of degrees. The prey is hit twice, once by the physical impact of the club and once by the collapsing cavitation bubble. Mantis shrimp can shatter aquarium glass. They can crack open the shells of clams, crabs, and snails with ease. Spearers, the other type, have sharp, barbed appendages that they use to impale soft-bodied prey like fish and worms. Their strikes are equally fast and equally lethal, but the mantis shrimp's most remarkable feature may be its eyes. Mantis shrimp have the most complex visual system of any known animal. While humans have 3 types of color-receptive cones in our eyes, allowing us to see red, green, and blue, mantis shrimp have 16 types of photoreceptor cells. They can see ultraviolet light, infrared light, and polarized light. Each eye can move independently and has trinocular vision, meaning a single eye can gauge depth and distance on its own. The visual world of the mantis shrimp is almost certainly richer and more detailed than anything we can imagine. What they see when they look at a coral reef, at the shimmer of sunlight through water, at the flash of a rival's display, we may never truly know. But it is, without doubt, extraordinary. Let us now descend once more to the deep sea to discuss a phenomenon that was once considered impossible: life in the hadal zone. We discussed the Mariana Trench and the Challenger Deep in the first part of this documentary, but the hadal zone encompasses far more than a single trench. There are over 30 trenches around the world that descend below 20,000 feet, and each one is a unique environment with its own community of organisms. The hadal zone was long thought to be essentially lifeless, too deep, too dark, too cold, too pressurized for anything to survive. But exploration in recent decades has revealed a surprising abundance and diversity of life. Amphipods, small, shrimp-like crustaceans, are among the most successful hadal organisms. In some trenches, they occur in enormous numbers, swarming over bait placed on the seafloor by researchers. Some hadal amphipods have been found with plastic fibers in their digestive tracts, a chilling reminder of the pervasiveness of plastic pollution. The deepest fish ever recorded is the Mariana snailfish, a small, translucent, tadpole-like creature found at depths exceeding 26,000 feet. It has no scales, a soft, gelatinous body, and a physiology that is exquisitely adapted to life under extreme pressure. At such depths, the pressure is over 1,000 times atmospheric pressure at the surface. Proteins and cell membranes that function perfectly at the surface would be crushed and distorted at hadal depths. The Mariana snailfish and other hadal organisms have evolved specialized molecules, including a compound called trimethylamine N-oxide, or TMAO, that stabilize their proteins under extreme pressure, allowing their cells to function normally in conditions that would be instantly lethal to surface-dwelling organisms. The discovery of thriving communities in the hadal zone has expanded our understanding of the limits of life and has fueled speculation about the possibility of life in the deep oceans of other worlds. Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath their icy crusts. These oceans are dark, cold, and under enormous pressure, conditions that are in many ways analogous to the hadal zone. If life can thrive in the deepest trenches of Earth's ocean, perhaps it can thrive beneath the ice of a distant moon. The ocean is not just teaching us about our own planet, it is teaching us where to look for life in the universe. Let us talk now about kelp forests, one of the ocean's most productive and ecologically important ecosystems. Kelp is a type of large brown algae that grows in cool, nutrient-rich coastal waters around the world. Some species of kelp can grow at rates of up to 2 feet per day, making them among the fastest-growing organisms on Earth. Under ideal conditions, kelp can reach heights of over 150 feet, forming towering underwater forests that rival terrestrial forests in their complexity and ecological importance. Kelp forests provide habitat for an extraordinary diversity of organisms. Fish, invertebrates, marine mammals, and seabirds all depend on kelp forests for food and shelter. The three-dimensional structure of the kelp canopy creates a layered environment with different species occupying different levels, much like the canopy, understory, and forest floor of a terrestrial forest. Sea urchins graze on the kelp, fish hide among the fronds. Sea otters wrap themselves in the kelp to sleep, anchoring themselves so they do not drift away with the current. Sea otters play a crucial role in the health of kelp forests, and their story is one of the most compelling examples of a keystone species in ecology. Sea otters are voracious predators of sea urchins. Without sea otters, sea urchin populations explode and the urchins overgraze on kelp, turning lush kelp forests into barren, rocky wastelands known as urchin barrens. When sea otters are present, they keep urchin populations in check, allowing kelp forests to flourish. This cascading effect, predator controls herbivore, which controls primary producer, is a classic trophic cascade, and it demonstrates how the removal of a single species can fundamentally alter an entire ecosystem. The near extinction of sea otters due to the fur trade in the 18th and 19th centuries led to the collapse of kelp forests across vast stretches of the Pacific coast. As sea otter populations have slowly recovered, thanks to protection and conservation efforts, kelp forests have begun to return. But the recovery is uneven and faces new threats, including warming ocean temperatures which stress kelp and the proliferation of sea urchins in areas where otter populations have not yet recovered. Kelp forests also play a role in carbon sequestration. Like terrestrial forests, kelp absorbs carbon dioxide through photosynthesis. When kelp dies, some of it sinks to the deep ocean floor, effectively removing carbon from the atmosphere for centuries or even millennia. Scientists are investigating the potential of kelp farming as a tool for carbon capture, as well as a sustainable source of food, animal feed, biofuel, and fertilizer. Now let us venture to the polar regions, where the ocean takes on an entirely different character. The Arctic Ocean, the smallest and shallowest of the world's 5 oceans, is a world of ice. For much of the year, the Arctic Ocean is covered by a layer of sea ice that can be several meters thick. This ice is not static. It grows in winter and shrinks in summer, driven by the cycle of freezing and melting that defines the Arctic seasons. Sea ice is far more than just frozen water. It is a habitat. The underside of Arctic sea ice is coated with algae, ice algae, that form the base of the Arctic food web. These algae are grazed by tiny crustaceans, which are eaten by Arctic cod, which are eaten by seals, which are eaten by polar bears. The entire food chain, from the smallest algae to the largest predator, depends on the ice. Without the ice, the chain collapses, and the ice is disappearing. The Arctic has warmed more than twice as fast as the global average, a phenomenon known as Arctic amplification. The extent of summer sea ice has declined by roughly 40% since satellite records began in the late 1970s. Some climate models project that the Arctic Ocean could experience ice-free summers within a few decades. The implications of this loss are profound for the species that depend on the ice, for the indigenous communities that have lived on and around the ice for thousands of years, and for the global climate system. Sea ice reflects a large proportion of incoming solar radiation back into space, a property known as albedo. Open ocean water, by contrast, is much darker and absorbs far more solar energy. As ice melts and exposes more dark water, the water absorbs more heat, which melts more ice, which exposes more water, which absorbs more heat, a positive feedback loop that accelerates warming. This ice albedo feedback is one of the reasons the Arctic is warming so rapidly, and it has consequences that extend far beyond the polar regions. At the other end of the planet, the Southern Ocean surrounds Antarctica and is, in many ways, even more extreme than the Arctic. The Southern Ocean is home to the Antarctic Circumpolar Current, the most powerful ocean current on Earth. This current flows continuously eastward around Antarctica, driven by the fierce westerly winds of the southern hemisphere, and it carries more water than any other current, approximately 150 times the flow of all the world's rivers combined. The Antarctic Circumpolar Current effectively isolates Antarctica from the warmer waters to the north, helping to maintain the continent's massive ice sheet. The Southern Ocean is also incredibly productive. The upwelling of nutrient-rich deep water supports massive blooms of phytoplankton, which in turn support enormous populations of krill, the small, shrimp-like crustaceans that form the foundation of the Antarctic food web. Antarctic krill are among the most abundant animals on Earth, with a total biomass estimated at several 100 million tons. They are the primary food source for whales, seals, penguins, and many species of fish and seabirds. The Southern Ocean's food web is in many ways a krill web. Everything revolves around these small, translucent crustaceans. Krill populations are sensitive to changes in sea ice because krill larvae feed on algae that grow on the underside of the ice. As Antarctic sea ice patterns change in response to warming, krill populations may be affected, with cascading consequences for every species that depends on them. A decline in krill could mean a decline in whales, seals, and penguins, a simplification and impoverishment of one of the richest ecosystems on the planet. Let us talk about something that connects the surface of the ocean to its deepest reaches, marine snow. We mentioned this phenomenon briefly in the first part of the documentary, but it deserves a closer look, because marine snow is the ocean's primary mechanism for transporting organic carbon from the surface to the deep. Marine snow is a continuous rain of organic particles that falls through the water column, dead plankton, fecal pellets, mucus, shed skin, fragments of plants and animals, and other detritus. These particles are typically small, a few millimeters at most, and they sink slowly, taking weeks or months to reach the deep ocean floor. As they sink, they are consumed, broken down, and repackaged by a succession of organisms in the mid-water layers. By the time they reach the abyssal plain, most of the easily digestible material has been stripped away, leaving only the most refractory compounds. Despite the loss of material during its descent, marine snow is the lifeline of the deep ocean. Almost all of the energy that fuels deep-sea ecosystems, with the exception of chemosynthetic communities around hydrothermal vents and cold seeps, comes from marine snow. The organisms of the deep sea are, in a very real sense, dependent on the scraps from the sunlit world above. The amount of marine snow that reaches the deep ocean varies with the productivity of the surface waters, the depth of the water column, and the activity of mid-water consumers. In some areas, particularly beneath highly productive surface waters, the rain of marine snow can be relatively heavy, supporting denser communities of deep-sea organisms. In other areas, beneath the nutrient-poor centers of subtropical gyres, the rain is sparse, and the deep-sea communities are correspondingly thin. Marine snow also plays a critical role in the global carbon cycle. By transporting organic carbon from the surface to the deep ocean, marine snow effectively removes carbon from the atmosphere for hundreds to thousands of years. This process, known as the biological pump, is one of the key mechanisms by which the ocean regulates atmospheric carbon dioxide levels. If the biological pump were to weaken due to changes in phytoplankton productivity, shifts in the composition of the planktonic community, or other factors, more carbon would remain in the atmosphere, accelerating climate change. Let us now explore one of the ocean's most visually stunning and ecologically significant phenomena, migration. We have already discussed the diel-vertical migration and the epic journeys of sea turtles, but the ocean hosts migrations of almost every conceivable scale and type. The gray whale undertakes one of the longest migrations of any mammal. Each year, gray whales travel approximately 10,000 to 12,000 miles round trip between their summer feeding grounds in the cold, productive waters of the Arctic and their winter breeding lagoons in the warm, shallow waters off the Pacific coast of the Baja California Peninsula. Pregnant females make this journey while carrying calves that weigh nearly a ton at birth. Migration takes several months in each direction, and the whales eat little or nothing during the winter breeding season, relying on fat reserves built up during the summer feeding binge. Humpback whales make similar migrations, traveling from polar feeding grounds to tropical breeding areas. Their journeys can cover over 5,000 miles each way. Along the way, male humpbacks sing their famous songs, complex, haunting sequences of sounds that can last for hours and be heard over vast distances. The purpose of these songs is still debated. They may serve to attract females, to establish dominance among males, or to maintain spacing between individuals. What is clear is that the songs are culturally transmitted. Males in the same population sing the same song, and the song evolves over time, with new phrases being added and old ones being dropped. Sometimes a new song element will spread from one population to another, crossing ocean basins over the course of a few years. This cultural transmission of song is one of the most remarkable examples of non-human culture in the animal world. Salmon migrations are legendary for a different reason. Born in freshwater streams, juvenile salmon make their way downstream to the ocean, where they spend years feeding and growing. When the time comes to spawn, they return to the exact stream where they were born, navigating across hundreds or thousands of miles of open ocean, entering the correct river system and swimming upstream, sometimes for hundreds of miles, against powerful currents, up waterfalls, and past predators. The effort is monumental, and for most species of Pacific salmon, it ends in death. After spawning, the adults die, their bodies decomposing in the stream and providing a crucial pulse of marine-derived nutrients to the freshwater and terrestrial ecosystems along the riverbanks. Trees growing near salmon streams grow faster than those far from the water, fertilized by the nitrogen and phosphorus brought from the ocean in the bodies of dying salmon. The ocean feeds the forest. The connections are everywhere. The Arctic tern holds the record for the longest migration of any animal on Earth. This small seabird breeds in the Arctic during the northern summer and then flies to the Antarctic for the southern summer, a round trip of approximately 44,000 miles. Over its lifetime, an Arctic tern may travel the equivalent of 3 round trips to the moon. It experiences more daylight than any other animal, living in an almost perpetual summer as it chases the sun from pole to pole. Let us turn now to a subject that is both deeply fascinating and deeply troubling: dead zones. These are areas of the ocean where oxygen levels are so low that most marine life cannot survive. Dead zones can occur naturally in some environments, but many of the dead zones we see today are caused or exacerbated by human activity. The primary culprit is nutrient pollution, the runoff of nitrogen and phosphorus from agricultural fertilizers, sewage, and industrial sources into rivers that ultimately discharge into the ocean. When these excess nutrients reach coastal waters, they fuel massive blooms of algae. When the algae die, they sink to the bottom and are decomposed by bacteria, which consume oxygen in the process. If the oxygen consumption exceeds the rate at which new oxygen is supplied by mixing, currents, or photosynthesis, the water becomes hypoxic, meaning it has dangerously low levels of dissolved oxygen. In severe cases, the water becomes anoxic, completely devoid of oxygen. Fish, crabs, shrimp, and other mobile organisms flee from dead zones if they can. Sessile organisms, those that cannot move, like mussels, oysters, and worms, simply die. The result is a stretch of ocean floor devoid of visible life, a marine desert created not by natural forces but by the excess fertility of human agriculture. There are now over 400 dead zones worldwide, and their number has been roughly doubling every decade since the 1960s. The largest is in the Baltic Sea, but significant dead zones also occur in the Gulf of Mexico, the East China Sea, and many other coastal areas around the world. The economic and ecological costs are enormous. Dead zones destroy fisheries, devastate coastal ecosystems, and undermine the livelihoods of communities that depend on the sea. The good news is that dead zones can recover. When nutrient inputs are reduced, oxygen levels can rebound and life can return. Several dead zones around the world have shown significant improvement following reductions in nutrient pollution. But achieving those reductions requires political will, economic investment, and a fundamental rethinking of how we manage our agricultural systems. The ocean, once again, is sending us a message. The question is whether we are listening. Let us talk about the narwhal, one of the most mysterious and magical creatures in the ocean. Sometimes called the unicorn of the sea, the narwhal is a medium-sized whale found in the Arctic waters of the North Atlantic and the Arctic Ocean. Males and occasionally females sport a long, spiraling tusk that can grow up to 10 feet in length. This tusk is actually a tooth, a canine tooth that grows through the upper lip and extends forward in a left-handed helix. For centuries, narwhal tusks were sold as unicorn horns, commanding enormous prices from European royalty who believed they had magical properties. The function of the narwhal's tusk has long been debated. It was once thought to be a weapon used in combat between males, but observations suggest that narwhals rarely use their tusks aggressively. More recent research has revealed that the tusk is, in fact, a sensory organ. It is permeated with millions of nerve endings that can detect changes in water temperature, pressure, and salinity. The tusk may function as a kind of environmental sensor, providing the narwhal with detailed information about the surrounding water. Some scientists have suggested that narwhals may also use their tusks to stun fish by striking the water surface, but this behavior has rarely been observed. Narwhals are among the deepest diving marine mammals, capable of reaching depths of over 5,000 feet. They spend much of the winter beneath the Arctic ice, surfacing to breathe in narrow cracks and leads in the ice. Their dependence on sea ice makes them particularly vulnerable to climate change, as the loss of Arctic ice alters their habitat, their prey availability, and their exposure to predators. Now let us consider the ocean's role in one of the most fundamental aspects of human civilization, global trade. Over 80% of global trade by volume is carried by sea. Container ships, bulk carriers, tankers, and other commercial vessels traverse the world's oceans every day, connecting producers and consumers across continents. The modern global economy is, quite literally, built on the ocean's ability to serve as a transportation corridor. The scale of maritime shipping is staggering. There are over 50,000 merchant ships operating worldwide, carrying everything from raw materials to finished goods, from food to fuel, from electronics to automobiles. The largest container ships can carry over 20,000 20-foot equivalent units, or TEUs, enough to fill a train over 40 miles long. If the contents of a single large container ship were transported by truck, it would require thousands of trucks on the road. Maritime shipping is, on a per-ton per mile basis, the most energy-efficient form of transportation available, but the sheer scale of the industry means that its total environmental footprint is significant. The global shipping fleet produces approximately 2 to 3% of the world's greenhouse gas emissions, comparable to the emissions of a major industrialized nation. Ships burn heavy fuel oil, one of the dirtiest fossil fuels, and their exhaust contains sulfur dioxide, nitrogen oxides, and particulate matter in addition to carbon dioxide. Efforts are underway to reduce the industry's environmental impact, including the development of cleaner fuels, more efficient hull designs, wind-assisted propulsion, and even fully electric or hydrogen-powered vessels. Maritime shipping also introduces invasive species to new environments. Ships take on ballast water in one port and discharge it in another, and that ballast water can contain the larvae, eggs, and microorganisms of species from the port of origin. When these organisms are released in a new environment, they can sometimes establish themselves and outcompete native species, with devastating ecological and economic consequences. The zebra mussel, the Asian shore crab, and numerous species of toxic algae have been spread around the world through ballast water. International regulations now require ships to treat their ballast water to kill or remove organisms before discharge, but compliance and enforcement remain challenging. Let us return for a moment to the sheer wonder of the ocean's inhabitants. The ocean sunfish, or mola mola, is one of the most unusual fish in the sea. It is the heaviest known bony fish in the world, with individuals weighing up to 5,000 pounds. Despite its enormous size, the ocean sunfish has a curiously compressed, almost circular body, and it swims with a distinctive undulating motion of its dorsal and anal fins. It feeds primarily on jellyfish, which are nutritionally poor, meaning the sunfish must consume enormous quantities to sustain its bulk. The ocean sunfish is also one of the most prolific spawners in the animal kingdom. A single female can produce up to 300 million eggs at a time, more than any other known vertebrate. The vast majority of these eggs and the larvae they produce will be eaten by predators, but the sheer volume ensures that at least some will survive. The mimic octopus, found in the tropical waters of Southeast Asia, takes camouflage and deception to an entirely new level. While many octopuses can change color and texture, the mimic octopus goes further. It changes its shape and behavior to impersonate other species. It has been observed mimicking the appearance and movements of at least 15 different species, including lionfish, flatfish, sea snakes, jellyfish, and shrimp. By flattening its body and undulating its arms in a specific pattern, it can convincingly impersonate a toxic flatfish, deterring predators. By trailing its arms behind it and swimming in a specific way, it mimics the banded coloring and movement of a sea snake. The mimic octopus assesses the threat it faces and selects the impersonation most likely to deter that specific predator. This is not simple mimicry. It is adaptive, context-dependent behavioral flexibility, a level of cognitive sophistication that is truly remarkable for an invertebrate. As we near the conclusion of our journey, let us address the future of the ocean and, by extension, the future of life on this planet. The challenges facing the ocean are immense: warming, acidification, deoxygenation, pollution, overfishing, habitat destruction, invasive species, noise. These are not future threats. They are present realities and they are intensifying, but there is also reason for hope. Around the world, scientists, conservationists, policymakers, and ordinary citizens are working to protect and restore the ocean. Marine protected areas now cover approximately 8% of the global ocean, and there is a growing international movement to expand that coverage to 30% by the year 2030. Research is advancing our understanding of marine ecosystems and the threats they face. Technology is providing new tools for monitoring, managing, and restoring ocean health. And awareness is growing. More people than ever before understand that the fate of the ocean and the fate of humanity are inextricably linked. The establishment of marine reserves, areas where fishing, mining, and other extractive activities are prohibited, has shown that the ocean can recover when given the chance. In the waters around certain protected islands, fish populations have rebounded dramatically within just a few years of protection. Coral reefs in well-managed marine parks have shown greater resilience to bleaching events than unprotected reefs. Whale populations, decimated by centuries of commercial whaling, have begun to recover since the international moratorium on commercial whaling was enacted in the 1980s. Humpback whales, once hunted to the brink of extinction, have rebounded to near pre-whaling numbers in some populations. Gray whales have made a similar recovery. These success stories demonstrate that conservation works, that the ocean, given half a chance, can heal itself. But conservation is not just about setting aside protected areas. It is about changing the way we interact with the ocean on a fundamental level. It is about reducing our carbon emissions to slow ocean warming and acidification. It is about managing fisheries sustainably so that fish populations can maintain themselves over the long term. It is about reducing plastic pollution at its source by redesigning products, improving waste management, and shifting away from single-use plastics. It is about treating our wastewater before it enters the ocean, reducing nutrient pollution and the dead zones it creates. It is about quieting the ocean so that whales and dolphins can communicate and navigate without interference. These are not impossible goals, they are choices, and they are choices that will define the trajectory of life on this planet for centuries to come. The ocean has been here for over 4 billion years. It has seen continents form and break apart. It has seen entire classes of organisms rise to dominance and then vanish. It has been frozen solid and heated to the boiling point. It has been bombarded by asteroids and racked by volcanic cataclysms. Through it all, it has endured, it has adapted, it has continued to sustain life. But the ocean we know, the ocean that supports the fish we eat, the climate we depend on, the biodiversity that enriches our world, that ocean is not guaranteed. It is not a given, it is a gift, and like all gifts, it can be squandered. There is a concept in oceanography called the ocean's memory. The ocean, because of its enormous thermal mass and slow circulation, responds to changes in climate on timescales of decades to centuries. The warming we see in the ocean today is, in part, a response to greenhouse gases emitted decades ago, and the emissions we produce today will continue to warm the ocean for decades to come, regardless of what we do. This lag effect means that the ocean's future is, to some extent, already determined. But the degree of warming, the severity of acidification, the extent of habitat loss, these are still within our power to influence. The ocean's memory also means that recovery, when it comes, will be slow. The carbon dioxide we have already added to the atmosphere and the ocean will take centuries to be fully absorbed and neutralized. The heat we have already added will take decades to redistribute. The species we have already lost are gone forever, but the ocean is patient. It operates on timescales that dwarf human lifetimes, human civilizations, human history. If we act wisely, if we act decisively, the ocean will recover. Not in our lifetimes, perhaps, but in the lifetimes of our grandchildren's grandchildren. We began this documentary with a simple observation. The ocean covers more than 70% of our planet. Let us end with another observation, equally simple and far more urgent. We depend on the ocean for every breath we take, for the food we eat, for the climate we live in, for the water we drink. The ocean is not a backdrop to human life. It is the foundation. Without it, there is no us. Every wave that breaks on every shore is a reminder. Every tide that rises and falls is a message. Every whale that breaches, every dolphin that leaps, every turtle that crawls up a beach to lay her eggs, these are not just natural events. They are invitations, invitations to pay attention. To learn, to care, to act. The ocean is the great unknown, the deep unknown, but it does not have to remain unknown. With every dive, every expedition, every research cruise, every new discovery, we are pulling back the curtain on a world that is more extraordinary, more complex, more beautiful, and more vital than we ever imagined. The question is not whether the ocean will survive. The ocean has survived everything this planet has thrown at it for 4 billion years. The question is, what kind of ocean will our children inherit? Will it be an ocean full of life, full of wonder, full of the abundance that has sustained humanity since the very beginning? Or will it be an impoverished ocean, depleted and degraded, a shadow of what it once was? That is our choice. And it is a choice we are making right now with every decision we make, every product we buy, every policy we support, every voice we raise. The deep unknown is calling. It is time to listen. The ocean covers our world. Let us not let it cover our conscience. There are creatures in the deep that we have not yet named. There are mountains on the ocean floor that no human eye has ever seen. There are currents flowing through the abyss that we have not yet charted. There are secrets in the water that could change everything we think we know about life, about chemistry, about physics, about the very nature of existence. The ocean is not just a place. It is a story. The longest, deepest, most complex story on Earth, and we are still reading the first chapter. Thank you for joining us on this journey. The ocean is vast, and our exploration has only just begun. Take what you have learned here and carry it with you. Share it, talk about it. Think about it the next time you see the sea, the next time you hear the sound of waves, the next time you taste salt on the wind, because the ocean is not out there, separate from us. It is in us. It is us. We are, every one of us, creatures of the sea. And the sea is waiting.